Okay, so there are two more problems to go. Let's consider this problem the shortest path problem. Given a network, we know the arc has a weight, which is distance. Okay? For each arc, we know its distance. We are asking from a given node S to a given destination T, what is the shortest path? Okay? That's the question. So, graphically, it may be something like this. We have several nodes, and several links. As always, we assume those links are directed, something like this. And for each arc, there is a distance, or maybe it's 2, 3, 1, 4, 1, 2, 3, 3, 1, 7, 8, 9, 10, 7, 6, 2, something like this. Okay. On this graph, we're asking what's the shortest path from S to T. Okay, one path is of course here. Okay, given any path, you may ask what's the distance, total distance, and we want to minimize such a total distance. Let's assume Dij are all non-negative. For some problems, there may be negative distance. In that case, of course, distance are something else, okay, or something like cost or whatever. Let's assume Dij are all non-zero in this course. So now the question is, how is a shortest path problem an MCNF problem? Of course, shortest path has some special algorithms. You're going to learn them in the algorithm course. But here, we will take a different approach. We will formulate the shortest path problem as an MCNF problem and then use the simplex method we can solve it. That's how we say a shortest path problem can be solved. The key is we simply ask how to send one unit from S to T. The reason for sending one unit is that we want to send a unit from S to T with the minimum cost. Then that one unit will try to find the minimum cost path, right? And that's the idea. So arc cost in an MCNF problem will just be those distances in the shortest path problem. There will be only one supply node S and one demand node D. All other nodes are transhipment nodes, and for supply and demand quantities, we will set them to be both 1. There are no arc capacities because we just want to send one unit, so that doesn't make any sense. That's not needed for we to have arc capacities. Okay, so again, this problem can be formulated as an integer program. Suppose T is the set of transhipment nodes. Then for our shortest path problem, it will be like this. Again, we want to minimize the total cost. But here, Xij will be either 0 or 1. We either go through arc ij or not. If we go through it, then the cost must be collected in our objective function. For the node S, for the source, the outgoing arc, at most, there must be one outgoing arc selected. For the destination T, at least one incoming arc must be selected. For other nodes, either both are 1 or both are 0. If both are 0, that node is not pathed. But if both are 1, then that node has an incoming arc and outgoing arc. Then it's pathed at the path is on the path. So again, if we need total unimodular, we have it. And here, for this problem is an binary program, right? Usually a binary program cannot be relaxed. But again, because it is an MCNF problem, relaxing this constraint leaves us a linear program relaxation that can be solved, that can generate an integer solution by the simplex method. So, shortest path problems can be done with our MCNF formulation. Good. So our last problem is the maximum flow problem. Given a network with arc capacities but no cost, we want to ask how many units may we send from a given source node to a given destination node T. So a graph may be something like this. Let's make it simple. So there are some arcs, some arcs, some arcs, some arcs. I'm not okay. For each arc, now there is no cost, but there are capacity. Maybe 4, 5, 6, 3, 2, 8, 2, 3, 7, 6, something like this. Then of course, now we want to ask from S to T, how many units may we send? One possibility is to just send through, for example, like this. Okay, this is one flow, and this is another flow. Okay, then here we can in total send 4 units because there is a bottleneck. This guy, only 4 units can be sent through this arc, through this path. For the bottom one, we can send at most 3 units. So for this plan, we can send 7 units, but we're not sure whether it is optimal, because maybe there is a way to send 9 units. We're not so sure. So it seems that there's none, but for a general graph, we want to ask what is the maximum flow we may send from S to T. How is the maximum flow problem an NCMF problem? Now we really need some creativity, because we want to send as many units as possible. So we are solving a maximum problem, not a minimization problem. Here, the key is the following. We want to send as many to T as possible, from S to T. So we're going to reward all those flows entering T by the following way. We will try to send units from T to S, from T back to S, with a negative cost. For example, suppose this is our network. Anyway, like this, S and T. For all those arcs, originally there is no cost, right? So in our MCNF formulation, we will say, okay, there are no costs. But for T to S, we will add one link. It does not appear in the past, but now we add one link, one arc from T to S with cost -1. If this is true, then we will try our best to send as many items into T as possible, right? So that we may pass through this route. As many as possible. So we will add that arc from S to T, which has unlimited capacity with cost -1. Any negative number is enough for us to send as many units into T as possible. All the nodes will be transshipment nodes. That means we don't have a supply, we don't have a demand nodes. All the nodes have a supply quantity 0. Okay? Because in general, after all, we will just be circulating on this circle. We just want to ask how many units may go through this arc. If we can answer that question, then we know how to send as many units from S to T as possible. Again, there is a formulation. Cost is -1 for the arc from T to S. And then for each node, the incoming arc and the outgoing arc, the incoming flow must equal the outgoing flow. So this is a negative, this is minus. We have capacity constraints, and in an IP formulation, they must be integers. Again, we can relax it because this is a totally unimodular coefficient matrix. Okay, so as a summary, we know MCNF, a special case is transshipment if there is no capacity. If there is no transshipment node, then it's a transportation problem. If all the supply and demand are 1 or -1, it's an assignment problem. For shortest path, it's a special case of transshipment. Now, there are some transshipment nodes. There is no capacity. But now, only the supply node has 1 unit of supply, and there's only one demand node which has one unit of demand. Okay, so for these problems, there are multiple supply and demand nodes. For it, there's only one supply and one demand. Finally, for maximum flow problem, is at another branch. There are arc capacities, of course, but there is no cost for all those original arcs. However, we add one artificial arc from T to S with cost -1. With that, maximum flow is just an MCNF problem. Okay, so in this lecture video, we basically focus on the mathematical part of MCNF problems and all those special cases. I hope that you will try to review this a little bit so that you are confident about what's the property of each special problems and what's their connections and how these special problems are MCNF problems. In the lecture, we will give you some concrete examples about real situations and help you to formulate them as MCNF problems. For example, I'm going to give you an inventory problem that can be formulated as a transportation problem. I'm going to tell you how a knapsack problem can be formulated as a shortest path. I'm going to tell you how a selection problem can be formulated as maximum flow, and for example, how project management can be formulated as a shortest path problem. Anyway, here we're done for theory. In the lecture, we will do applications. Both of them are important. I hope you will enjoy it. That's it. Thank you.